first example, we are going to find the volume of the solid obtained by rotating the area bounded by y equals x squared, y equals 0, and x equals 2. We're going to rotate that about the x-axis. Okay, so it is definitely sketch time. First things first. That is our first step here. We're going to sketch the region that's going to get rotated. All right, so set yourself up a little graph here. Okay, and check out our functions. Okay, so we've got y equals x squared. All right, so graph that parabola. 2, 4, that's about all I can fit. Okay. So there's the parabola. There would be this other side to that as well. All right. Then our next boundary here is y equals 0. Okay, so y equals 0 would be the x-axis. So this is also a boundary. And then our last boundary is x equals 2. So that would be right here, vertical line. Okay, so we want to take the area bounded by those 3 graphs. And notice that those come together here at the origin and they come together up here at the point 2, 4. All right, so it turns out that the area bounded that we're looking at is this area right in here. Okay, so we actually didn't need this other half of the parabola over there. All right. So we're going to take this kind of ramp-shaped area there, and we're going to imagine rotating that around the x-axis. Okay, so this is really hard to do over the internet here to communicate to you, but imagine this black shaded area there coming out from the screen, sweeping around in a circular shape. It's going to run back into your screen again, so it's going to kind of smack the screen again down here. All right. And then it's going to keep rotating back behind the computer screen until it makes a full circle. Okay, so if you can imagine what that looks like, it's going to be kind of like a cone or a horn type shape with a curved outer edge like this. That's coming from that parabola. But it's 3-dimensional now. Okay, and the bottom has gone all the way around in a circle. So it's going to look something like this. It's got this circular base to it, and then these slanty sides. Okay, so there's like coming through the middle there, that's where the x-axis would be. But this is like a, yeah, like a big, like the end of a trumpet or something like that, but it comes to a point right here. All right, little hard to picture, I know. So let me switch over to the internets really quick, and I'll show you a website that can actually draw these solids of revolution better than I can. Whoa, surprise. Bet you didn't think anything could get better than that. But here, let's switch over real quick. All right, so let me see if my keyboard will cooperate with me. Okay, here we go. So the website is shodor.com. untitled.org. I do not know why it's called that. And I will post this link for you guys so that you can use this website as well. Okay, so here we are. So yeah, this is a function revolution visualizer. So here, they have the possibility of using two different functions, which, yeah, we are actually going to want to do that because we have a couple different things that are bounding our region here. All right. So our first function that we're looking at here is y equals x squared. So we're going to put that in. X, where is the exponent button? There we go, x squared. Okay. And then for our second function, notice how it does say leave blank for disk method. You can do that, or you can put just a 0 in there instead. That's for the line y equals 0 that was also bounding our area. Okay. And click set functions. Oops. Let me make sure that's the lowercase x. I think it might be having a bit of a fit there. There we go. There's our parabola. Okay. So we want to also kind of nip in the x direction here. It's going right now from -15 to +15. Here we only want to go from x equals 0 to 2 because that's where our area really was. Let me pop back over to our graph here. Yeah. So yeah, notice how we don't want to go all the way from x equals -15 to +15. Our area that we're looking at only goes from x equals 0 to x equals 2. That's why I changed that last part there. Okay. So back to the visualizer. So here, they've graphed our little portion of the parabola and the little horizontal portion of the x-axis that's bounding our area. Notice that they didn't put in the vertical line x equals 2. I think it's just hard for the visualizer here to graph those vertical lines, but it is cutting off the area there at x equals 2. It is really tiny looking at that also. So up here there is a set window option where you can change that and zoom in a little bit. So I'm going to take our x value from -1, enter, oops, crap, -1, thank you. Sorry, this is having a hard time. There we go, -1. And then for our maximum x value there, technology, I'm going to have it go up to 3, a little bit past our actual boundary itself. And for the scale, that's just how much is each tick mark worth. So I'm going to make the scale 1 unit there. Each tick mark will be 1 unit on the graph. And then for our y's, I'm going to set a slightly smaller window that way as well. I'll just go -5 to +5 and scale the y-axis by 1 as well. Okay, set and close. There we go. That way we can see our bounded area a little clearer there. Okay. So yeah, now we can see that that area that they're bounding off in red, that actually is stopping at equals 2. We've got this point up in the corner here at 2, 4, and it is stopping at the origin also. So that matches up with what we had graphed. So that's good. Okay, now the fun bit is actually revolving this area about the x-axis. And so you go down here to this box that says revolve. And here you can decide whether you want it to go fast, medium, or slow. I'll just set it to medium. And we are going to revolve this about the x-axis. So the line y equals 0 is the x-axis, and we've already got that selected there. Okay, so when that is all good, then you're going to click this button right here that says revolve and watch the graph there. Ready? Okay, so that is the rotation that I was trying to describe to you guys, how it rotates around in a full circle. It takes the bounded area and rotates it around. And then the fun thing is that we can take this solid, that kind of horn-shaped looking thing that I was trying to draw, and you can actually drag it around and see what that shape looks like. So we can see that, oh yeah, the bottom of it made a big full circle. It comes up to a point there. And even though this looks hollow, that is actually solid all the way through. It's because I've got it set to wireframe up here. So you could set it to solid as well. The animation though on this, I think even when you click solid, it still looks a little wonky. So you just have to know that that really is all the way filled in. This is not hollow. Okay. So yeah, there's the view looking down from the top of this thing. All right. Kind of like a gramophone. Interesting. Okay. Yeah, and Felipe, what you're talking about in the chat there, that's accurate. It's the largest radius that we have on this is a radius of 4 along the huge circular bottom there, or I don't know if I would say it's huge, but it is a radius of 4. That is the largest radius we have, and you're right, it is shrinking to make that horn shape. Perfect. Yeah, so our biggest radius is 4, and then it actually shrinks down to a radius of 0 up at the point of the horn there. Or if you're looking as we go from x equals 0 to 2, you start with the radius of 0 and then it grows out to that big radius of 4 there. So yeah, that's what we're looking at. But you are totally right. The radius is changing as we move through the different x values on this graph. Okay, so let's take that visualization there now that we know what our solid looks like, and we're going to go back and look at the volume of this. Okay, so we've sketched our solid. We could also sketch a typical cross section just to see what that would look like here. So we're going to be taking this horn and making little slices out of it. Okay, so you might take your sharp knife or whatever and slice down this way across the horn. And we're going to remove a typical cross section there. So typical cross section. Since this is fully shaded in and it's a solid object, we call this a disc. So this is the disc type and not the washer type. There is no hole in this horn. It's a ineffective horn. It's solid all the way through. Okay, so this is a disc, and it would look something like the little penny type shape we had drawn before. All right. It has a certain radius associated with it, and it has a certain thickness, okay, associated with it. Okay, thickness or height there. And so yeah, the volume of that tiny little cross section is going to be our cross-sectional area times the height, okay? Or you could say pi r squared h. Okay, but here, like Felipe was mentioning, the radius is shrinking as you're looking from right to left, or it's growing if you're looking from left to right. The overall concept there is that the radius is changing, okay? So we need to figure out how to calculate that radius at any x value. So how would you find the radius for each x value? Like if, you were at some x value, whatever it might be, how would you get that radius right there? Any thoughts? Yeah, Brandon, good. Plugging x into the equation to get y. Exactly. Because yeah, we know what equation that is that's making that outer curve of the horn. It's the parabola y equals x squared. And so we can use that to find the radius because the radius is determined by whatever value the parabola has at that point. All right. And so, yeah, we can see that the radius, if we use that equation, it's going to change appropriately like we're seeing here. When x equals 0, there's a radius of 0. That's right at the tip there, tip of the horn. If x equaled 1, we would have a radius of 1 unit. That matches up right here. If x equals 2, we're going to have that biggest radius, that full radius of 4 when x equals 2. So yeah, that's exactly where our radius comes from. The radius is x squared. So this is determined by the parabola. All right. So our little delta v expression, we could write as pi r, we can find by doing x squared. So that is r squared. Okay, I'm going to highlight that. R goes here, R gets replaced by x squared. Okay, so pi r squared, and then h is, again, a little tiny change in the x direction. So h is some sort of delta x, and we can write that like that. So for our individual little change in volume, we have pi x squared squared times delta x, or you could rewrite that as pi x to the 4th delta x. Okay, cool. All right. And then we've got our delta v expression there. Let's see what we were going to do next. All right, we just did step 2. We found cross-sectional area by doing that pi r squared, and that led us to delta v. Okay, so we got that good. Step 3 is to find our limits of integration. So what x values are we going to integrate across? What's our smallest x value and largest? Yep, Brandon's on it again. We're going to go from 0 to 2. Nice. So limits are x equals 0 to 2, because that's the full area that made our horn shape here. Okay, so yeah, we got our delta v, we got our limits. That's going to let us set up our integral to find the volume. So since we're doing this one with respect to x, we're going to use this formula right here. Go from a to b, a of x dx. All right, so this is our volume integral. We're going from 0 to 2. And inside, you just put your little delta v expression there. All right, because that already incorporates the cross-sectional area. So we'll have pi x to the fourth. And remember, inside an integral, you don't write delta x, you write dx. Okay, to show that variable of integration. Okay, so the hardest thing about these really is getting the integral set up. Now that we actually see the integral, it's not too crazy to compute this one. Notice that you can pull the pi out of the integral because it's a constant. So you could go pi 0 to 2 x to the fourth dx. And then you'd need to do the antiderivative of x to the fourth. And we're going to plug in those limits. So again, don't hassle with Riemann sums on these. This would be nuts to try and do by a Riemann sum because you've got like x to the fourth power. So we are not doing Riemann sums here. We're using fundamental theorem of calculus. All right. Just to make that very clear before anyone puts way too much work on themselves. Okay. So we're plugging in first the upper limit and then the lower limit of integration. Lower limit is 0, which is really nice. That part just drops out. And then 2 to the fifth is 32. So if we do our calculation on that, the total volume of this shape is going to be 32 pi over 5 cubic units. Okay, so 32 pi over 5 for the volume of that horn shape. All right. And if you want to verify your answer on these, that website also does a volume calculation. You can see right here. They do it decimal style, so they have a volume of 20.106. But if you type in on your calculator 32 pi over 5, it'll turn out to be about 20.106 to that many decimal places. So yeah, we end up getting an answer that agrees. Okay, so yeah, again, hardest thing on these is visualizing the shape and coming up with the integral. Once you get to the integral itself, it's usually not too bad from that point on. But yeah, getting there can be hairy sometimes.